Okay, good morning, everyone. So let me continue the Sahan-Banach separation theorem. So in the last class, we proved this proposition that if C is a non-empty open convex set in a real nonlinear space and x0 is a point not in C, then we can find the bounded linear functional f such that f of x is less than f of x0 for all x in C. So we will use this to prove the following Hahn-Banach separation theorem. So here we are given A and B. These are two non-empty and disjoint convex sets in a real nonlinear space. Let's call it V. And we assume that one of them is open. So then the claim is that there exists a closed hyperplane which separates A and B. So what is the meaning of this? So we know that a closed hyperplane is given by x such that fx is equal to alpha for some real number alpha. Right? So where f is bounded linear functional. So this means that there exists some f in V star and alpha in R such that fx is less than equal to alpha is less than equal to fy for all x in A and y in B. So this is the meaning that a closed hyperplane separates A and B. So if you look at the hyperplane in this case, it is a, a hyperplane given by fx equal to alpha, and then we are saying that for every x in A, fx is less than equal to alpha. That means that and fy is bigger than equal to alpha. So this A and B are on the opposite sides of this hyperplane. So this is the geometric meaning. So this is that's why this is called this Hahn-Banach separation theorem. And we used the Hahn-Banach theorem for the previous proposition. So we'll make use of that last proposition to prove this result. So we are given A and B are disjoint convex sets. So suppose we take C to be the difference of A and B. So let C is equal to A minus B. Where what is the meaning of this A minus B? This is not the set difference. This is because these are in a vector space. So I can take this to be equal to x minus y, where x is in A and y is in B. Right. So if I take any arbitrary point in A and a point in B and take the difference and collect all such things. So this is my set C. So now what can you say about this set C? We are given that A and B are convex. So if A and B are convex sets, then the sum and difference, this will also be convex, right? So since A and B are convex sets, it is easy to show that C is also convex. You should try to prove this. This is very easy. You just take any two arbitrary point in this set C, and then you have to show that the convex combination also belongs here. So if you take any 2 points, say x1 minus y1 and x2 minus y2 belonging to C, and then if you take any t between 0 and 1, then you have to show that t times x1 minus y1 plus 1 minus t times x2 minus y2, that is also in C. But that is same thing as t times x1 plus 1 minus t times x2, which is in A because A is convex, minus t times y1 plus 1 minus t times y2. Again, B is convex, so that is also in B. And then this point is in A minus B. So that means it is in C. So sum of two convex sets or difference of two convex sets is also convex in a nonlinear space. So we get this in any vector space, you can say this. So C is convex. Also now we are given that A is open. So because A is open, the C will also be open. Why? Because you see the C can be written as union of A minus singleton Y, where Y belongs to B. Right? So we can write this C as union of for these sets A minus Y, and because A is open, so therefore A minus singleton Y, this is also open. So is open because A open implies A minus singleton Y is open for all Y.
So that is union or intersection?
Union. Y intersection. Is it not correct? Is it okay? See, any point in C can be written as x minus y, where x is in A and y is in B, right? So if you look at A minus y, what is this? This is all the points of the form x minus y for this fixed y. And then if you vary y also, then you will get all the points of the form x minus y, where x is in A and y is in B. So this is union. And you know that arbitrary union of open sets is open. So therefore, this is C will be open because all of these are open.
Okay.
Is it okay? So now we get C is open and convex set. So hence C is a non-empty, because A and B are non-empty, so C is also non-empty. So this is a non-empty open convex set in V, and you know that A and B are disjoint, since A intersection B is empty, 0 is not in C, right? 0 will be in C. If 0 can be written as x minus y, where x is in A, y is in B, that will mean that x is equal to y. So that is the only possible if there is something which is in the intersection. So because these are disjoint, this origin is not in this open convex set C. So now we get a non-empty open convex set and a point which is not in C. So now we will apply the previous proposition. So by the previous proposition, we know that there exists some f in V star such that f of for every point in C, f of x is less than f of x naught. But what is f of x naught? F of x naught here is f of 0, which is C. So this will mean that there exists f such that f of z is less than f of 0, which is 0, for all z in C. But C is A minus B. So this implies f of x minus y is less than 0 for all x in A and y in B, which implies fx is less than fy for all x in A and y in B. So f of x is strictly less than f of y if you take any x in A and y in B, and therefore what alpha you can choose. So this also implies that supremum of if I take fx, x belonging to A, this will be less than or equal to infimum of fy, y in B. And when you take the supremum and infimum, it may be equal also. So we get this. So you choose any alpha which is between these two numbers, and that will do. Choose alpha in R such that this supremum is less than equal to alpha is less than equal to infimum of fy for y in B. Then fx is less than equal to alpha is less than equal to fy for all x in A and y in B. So this is what we had to prove. We had to prove that there exists some alpha and some bounded linear functional such that fx is less than equal to alpha less than equal to fy for all. Here note that we may not be able to separate this strictly. So we may not have that fx is strictly less than alpha and less than fy for all x in A and y in B. Because though we know that for any 2 points fx is strictly less than fy, but there may not be any alpha such that this is true for strict inequality holds for all x in A and y in B. So, but we will see that if under some more condition we can guarantee the strict separation also. So that is our next theorem.
Sir, according
Yes.
to the last statement, there can be an alpha for which corresponding to which for some x in A and for some y in B, this can be equal, right?
Right.
But above that, you have written that fx is strictly less than fy for all x in A and for all y in B.
Right.
But we are getting, matlab we may get some particular x and y, so that fx is equal to alpha and equal to fy.
No, no, you may not. I mean, you will not get by this inequality. You won't get fx equal to fy, right? But what can happen is that it may be that fx is equal to alpha, which is strictly less than fy, or it can be that fx is strictly less than alpha equal to fy, right? So this alpha may be equal to fx or fy. It cannot be equal to both fx and fy.
Okay, okay, sir. Yes.
Is
Okay.
it okay? So what I am saying is that I mean, you cannot have strict inequality. Both of these cannot be strict inequality. So it may be that one of them is equality. Of course, both equality also is not possible by this. Okay. Okay. So now let me prove the other theorem. So this is also called Han-Banach theorem. So here also we have two non-empty disjoint convex sets. So let A and B be two non-empty disjoint convex sets in a real nonlinear space B. And now here we will assume, in the previous theorem we assumed that A is open and there is no condition on B. So only if we assume that one of them is open, then we can guarantee that previous conclusion. Now here we will assume that one of them is closed and the other one is compact. So assume that A is closed, say A is closed and B is compact. So in this case, we can separate strictly by hyperplane. So then A and B can be separated strictly by a closed hyperplane. So that is, there exists some f in V star and alpha in R such that, so also and some epsilon positive such that fx is less than equal to alpha minus epsilon and fy is greater than equal to alpha plus epsilon for all x in A and y in B. So here we are saying that there is some epsilon such that fx will be less than equal to alpha minus epsilon and fx is bigger than equal to alpha plus epsilon. In the previous theorem, we only said that there is some alpha such that fx is less than equal to alpha and fy is bigger than equal to alpha. Right? Here we are saying that we can make fx to be less than equal to some number smaller than alpha and fy to be bigger than equal to some number bigger than alpha. So in particular, fx is strictly less than alpha and fy is strictly bigger than alpha. So let us prove this. So we would like to apply the previous theorem. So the previous theorem says that if we have non-empty disjoint convex sets and one of them is open, then we can separate by a closed hyperplane. So here, because I have A and B are convex sets, they are disjoint, and one of them is closed and another is compact. So then there exists some neighborhood of A and a neighborhood of B. So open neighborhood of A and B, which are also disjoint. So and convex also. So how do we get that? So if we take any eta positive, then if we look at A plus the open ball of radius eta centered at the origin, and similarly B plus d0 eta. What can we say about this? So then this and this are non-empty open convex sets where this d0 eta is the open ball of radius eta centered at the origin. So is it clear? Because the A and B are non-empty, therefore these sets are also non-empty. Why they are open?
Like we can consider A plus D0 eta as union of X in A dx eta, which by definition will be open.
Yeah, exactly. So this is exactly like what we did in the previous one. We said that if one of them is open, then and you add another set, then it will be open, right? So because d0 eta is open, then you are adding the points of A, so that will also be open, right? So any translate of open set, so that is simply like you said, the d of x comma eta where x belongs to A, and then we take the union of that x belonging to A. So union of open set is open, so therefore this is open. So these are open sets, and why they are convex? That is again because these are sum of two convex sets, right? So A is convex and d0 eta is also convex. So sum of two convex sets, that is again convex. So these are convex also. So now we get non-empty open convex sets. So now if we can have that these sets are also disjoint, see, they will not be disjoint for any eta, right? We are only given that A and B are disjoint. So if we can make these disjoint, then we can use the previous theorem and get some alpha such that we get that fx and fy are fx is less than equal to alpha and fy is bigger than equal to alpha for all x in this set and y in this set. So first of all, we want to make sure that there exists some eta small enough such that these two sets are disjoint. So for that, we will make use of the fact that A is closed and B is compact. So let me write this claim. A plus D0 eta and B plus D0 eta. These are disjoint if eta greater than 0 is sufficiently small. Then we will choose that eta and then work with that. So why is this true? So suppose this is not true, then what happens? Then for every eta, we are saying that these sets are not disjoint. So there exists some point which is in both of these for any eta. So in particular, if I take say a eta equal to 1 by n, then corresponding to that, I'll get some point which is in the intersection of both these. So if this is not true, then for every n in n, there exists some point which is in the intersection. So let's call that Zn belonging to A plus D 0 1 by n intersection B plus D 0 1 by n. Right? So what does this mean? If Zn belongs to A plus D 0 1 by n intersection this, so this implies there exists xn in A and yn in B such that this Zn is equal to let me write like this. So Zn minus xn, this belongs to D0 1 by n and Zn minus yn belongs to D0 1 by n. Is this clear? Because if Zn belongs to this, then Zn can be written as xn plus some point in D0 1 by n. So that means that Zn minus xn, that is in D0 1 by n, and similarly Zn minus yn is in D0 1 by n, where xn is a point in A and yn is a point in B. So if Zn minus xn belongs to this and Zn minus yn belongs to this, then this implies what? What can we say about xn minus yn norm? This is same as Zn minus xn minus Zn minus yn norm. but Zn minus Xn norm is less than 1 by n, and this is less than 1 by n. So this will be less than 2 by n. So norm of Xn minus Yn is less than 2 by n. So this implies norm of Xn minus Yn, this goes to 0 as n goes to infinity. So assuming that those two sets are disjoint, we are able to find a sequence in A and a sequence in B such that the distance between these two goes to 0. Now we will make use of the fact that A is closed and B is compact. So Yn is a sequence in B and B is given to be compact. So since B is compact, the sequence Yn has a convergent subsequence say Ynk converging to some point, let's call Y in B. Right, so we get a convergent subsequence of this Yn converging to a point Y. So then we get Ynk converges to Y, and we are given this thing that Xn minus Yn, this goes to 0. So this will imply Xnk must also converge to Y. Right, because Xnk is nothing but Ynk plus Xnk minus Ynk, and that thing goes to 0. This goes to Y and this goes to 0. So therefore Ynk will converge to Y. So this means that Y is the limit point of A, but A is given to be closed. So since A is closed, we must have that Y belongs to A. So what we got, this Y, this limit is in B as well as A. This implies A intersection B is non-empty, which is a contradiction. So hence the claim is true. So now we got that for small enough eta, we have so there is some eta such that these are disjoint. So let eta greater than 0 be such that this A plus D0 eta and B plus D0 eta are disjoint. Then we will apply the previous theorem. By the previous theorem, now we have open, convex, non-empty disjoint sets. So the previous theorem says that there exists f in V star and alpha in R such that f of let me call this as we want to use x and y. So f of any point in a plus this d0 eta. So f of it's called z is less than equal to alpha is less than equal to f of w for all z in a plus this open ball and w in b plus d0 eta. What we had to show that there is some epsilon such that fx is less than equal to alpha minus epsilon for all x in A, and for all y in B, fy is bigger than equal to alpha minus epsilon. So from this we will try to get that. So therefore, if x is in A, y in B, and say z1 is anything in B0, in the closed unit ball, z1 and z2 if I take, this is the closed unit ball. So then f of x plus, if I take eta by 2 times z1, then x belongs to A and eta by 2 z1, this belongs to d0 eta. So therefore, this is less than equal to alpha and this is less than equal to f of, if I take y plus eta by 2 times z2, then we get this. So this is by the previous inequality. So from here, what can we say? So that is fx plus eta by 2 f of z1 is less than equal to alpha is less than equal to fy plus eta by 2 f of z2. Now if I take this supremum of this left hand side for all z1 in the closed unit ball, then what is the supremum of f of z1 where z1 belonging to b01? That gives exactly the norm of f, right? Norm of f is supremum of mod fz where z belongs to the closed unit ball. So we'll get fx plus eta by 2 norm f is less than equal to alpha, and similarly if I take the infimum of this f of z2, where z2 belongs to b01. Then what is the infimum of f of z2, where z2 is in closed unit ball?
Zero.
Minus.
Why 0? Minus
Negative.
of norm f,
Minus.
right? Yeah.
Minus of normal.
Right. So now taking supremum of the left hand side over z1 belonging to b01 and infimum of the right hand side over z2 belonging to b01, we get f of x plus eta by 2 norm f is less than equal to alpha is less than equal to fy minus eta by 2 norm f. So that means we are done, right? What we wanted. Therefore, the theorem is proved. Or epsilon I can take as eta by 2 norm f. Then fx is less than equal to alpha minus epsilon, which is this thing, and fy is bigger than equal to alpha plus epsilon. For epsilon equal to eta by 2 norm f, we get this. So any doubts so far?
No.
So here we assume that one of the set is compact and another is closed to get this.
So for the claim you made, I actually had an alternate proof in mind.
Yeah.
So like yeah. So in the claim, yes, sir, this claim. So like here we are given that like A is closed. So like we know that A complement is open. So for
Right.
every y A complement, I can choose a radius eta y such that dy eta y is a subset of A complement itself. And now since B is also a subset of A complement, I know that these open balls now they cover B, and since B is compact, I can choose a finite subcover of these open balls,
Mhm.
and then suppose if I choose say n such balls, then I can take that eta to be min of
Union.
eta
Yeah.
eta n.
Yeah, see, I mean, in general, like a topological space, also you can prove that if you have uh, a Hausdorff topological space and you have a closed set and a compact set, then you can separate that by open neighborhoods, right? So, that is the usual thing, like if you have seen in topology. So, what you will do is that for every point you first find neighborhoods such that these are disjoint, and then you get an open cover of this set B, and then you can take a finite subcover, so that uh, will give you this thing. So, I mean, we get neighborhood, but here we want to find like of this form, neighborhood of this form A plus. So this some open ball and B plus that open ball. So that is why like I have done like this, right? So because here we have non-linear space. So in general, in any like separate them by disjoint open sets. Is it okay? I mean, you can try and write like your proof and see whether that works here or not.
But that like we can separate, so how we prove that that will be convex?
Exactly. So that is not. So that is why we want something of this form, that A plus an open ball, right? So we don't want like any like neighborhood. We want a neighborhood of this form. We want this open and convex sets, right? So that is why we have done like this.
Sir, this non-linear space would be a normal topological space, right?
Yes.
So by the T4 axiom, we can obtain open balls containing A and B. So they will be convex also.
Yeah, you can use some other results and then do this. See, because in normal this thing you can use that Orison's lemma. So if you have uh, in fact two closed sets, you can separate by open sets, and
And they will be balls, so they will be convex.
no, I don't know. In general, you cannot say that you can separate by balls, right? Because that theorem only says that there exist some open sets containing A and an open set containing V, such that the intersection is empty, right? But then you will have to guarantee that there exists some open ball inside that open set, uh, which also contains A and similarly B, and then you can do so. So I don't know like directly whether you can say like that. So this thing, I mean, what we are asking is that suppose we don't have non-linear space, we only have any metric space, and then we have a closed set and a compact set. Then can we separate them by the disjoint open balls containing A and B? So that I am not sure if it can be done in a general metric space, because here like we are making use of this norm linear space. So, because if you don't have like something like this addition, then we won't be able to say this, right? So I don't know, it may work in more general things also. For example, I think if you have like topological vector space, there it can work, because you need some vector space structure to add these sets, and then if you have some topology, then it may be possible to like prove similar things in more general things also. So, but we are not like studying more general like topological vector spaces. You can look at like Rudin's functional analysis book, where they talk about this topological vector space, and there are like these Han-Banach theorems for general topological vector spaces also, it is true. So okay, but we will not discuss that, because then I have to like do many other things. So I think I'll just do a corollary to this, and then we can stop. So suppose we have a subspace W, of a real nonlinear space V, and here we are all like working with only real nonlinear space. You can have like versions of these things for complex nonlinear space. In that case, this like fx less than equal to alpha, you can replace by real part of f, and then you can do. So again, I am not doing those things. Maybe I may give as tutorial problems for you to try. So W is a subspace of real nonlinear space V, and assume that W is not dense in V. So W closer is not equal to V. Then there exists F in V star such that F is not identically 0. So this is a non-zero bounded linear functional, and Fx is equal to 0 for all x in W. See, if Fx equal to 0 for all x in W for some continuous linear functional, and if W is dense in V, then Fx will be 0 for all x in V also, right? Just by using the continuity and density. But here we are assuming that W is not dense in V. So then we are saying that we can find the bounded linear functional, a non-zero bounded linear functional, which is 0 on whole of W. So to prove this, suppose we take any point x naught belonging to V minus W closer. So we know there exists some point in V which is not in W closer. So we take that and let A is equal to W closer and B is equal to singleton x naught. Then our set A is closed, B is compact, and x naught is not in W closer. So therefore A intersection B is empty. So A is closed, B is compact. They are non-empty and disjoint. Also, singleton is obviously convex, and because W is given to be a subspace, any subspace is always a convex set, and then if you take the closure of that, that is also convex. So these are also convex. So also A and B are convex sets. So now we can apply the previous theorem. We get a closed set, a compact set. Both are convex, non-empty and disjoint. So we can separate this. So therefore, by the previous theorem, there exists F in V star and alpha in R such that Fx is less than alpha is less than Fy. So Fy is simply f of x naught. So Fx is less than alpha, which is less than Fx naught for all x in A, which is W closer. So for every x closer, we have Fx is less than alpha and this is less than f of x naught. So there is only one point in B. Now, right. So now, do you see that this will satisfy that f of x is equal to 0 for all x in W? So since
Yes,
W,
otherwise we can.
W is a subspace, right? So first of all, 0 is in W. So therefore, alpha is greater than f of 0, which is 0. So alpha has to be positive, right? And then we are saying that fx is less than alpha for every x in W closer. So it is also in for every x in W, it has to be less than some fixed thing. So if f is non-zero, then at some point it will be is some positive number, and then you can multiply by t to make it arbitrarily large, right? So therefore it cannot happen, right? So right, so we can say that for any x in W, and suppose I take any natural number n, then f of nx has to be less than alpha. So this will imply fx is less than alpha by n. This is true for every n in n. So this will imply that fx has to be less than equal to 0. Right? So fx has to be less than equal to 0 because alpha by n goes to 0. But then you can replace x by minus x. So fx less than equal to 0 for all x in W. So this will imply that if I take f of minus x, that is also less than equal to 0 for all x in W. But this implies fx has to be bigger than equal to 0 for all x in W. So therefore fx has to be 0. Right, so this is just because it is a subspace, you can always like replace by negative or any multiple and then do that. So we get f such that fx equal to 0 on W, and because f of x naught is bigger than this alpha, which is positive, so f of x naught is strictly bigger than 0. So therefore f is non-zero. So this f satisfies this condition. Okay, so we will stop here. I think in the next class we will discuss these other important theorems of functional analysis. So that is open mapping theorem, closed graph theorem, and then there is this uh, Banach-Steinhaus theorem. So those things. So for that we will need this bare category theorem, which I hope that you must have seen in your real analysis course. So I'll recall the bare category theorem. If needed, I can do the proof also, but that I hope that you would have seen it before. So that bare category theorem will be very useful for the next few theorems that we will learn. Okay. Any question before we stop?
So in this like corollary, can we also prove it using the first version of Hahn-Banach separation theorem? Like if I take an like I know that W closure is not V.
Right,
So
right.
like I can take one open set to be the complement of W closure.
Okay. No, see the previous one, you can says that if you have any like bounded linear functional on a subspace, then you can extend it to the whole thing, right? So
no, the previous version of this separation theorem only,
okay,
where
okay,
you have an open set and then you just have an arbitrary disjoint convex set.
right, right, right.
So sorry, no, not so like if we take the something like interior of W and we take one element in the complement of W.
If you take the
I take the open set to be the interior of W.
that will not work because you see if you have any like proper subspace, then interior it will be empty, right?
Yeah, then maybe we might need to take some relative
Because
interior.
yeah,
Like,
because if you have any like if you have a subspace, proper subspace, then it is say interior is always empty, because if you have any like open ball contained inside that subspace, then by multiplying by arbitrary scalar, you will get that it has to be whole space only. So
oh, yes, yes, yes. No, maybe if we can take the relative interior will also be open.
I mean, we won't be able to apply that previous one, right? Because we will need. So I don't know. You can think about it and then maybe let me know later if you think that it can be done. Of course, like if I take W to be a closed subspace of V, and then uh, suppose closed proper subspace, then we can say this thing by using Hahn-Banach extension theorem also. So that is you can look at in that case V mod W, the quotient space, and then you can work on that. So that is like one I think I did not do that application of that Hahn-Banach extension theorem. So maybe in the tutorial I'll put that problem. So if this is a closed proper subspace, then you can do it directly, because in that case the quotient space, that will be a non-linear space, and then you can apply that Hahn-Banach extension theorem on that. So a corollary of that we said that if we have any point outside uh, then we get yeah, so we get a bounded linear functional such that f of x naught equal to norm of x naught, right? So we can use that thing. So okay, one more thing, Dheeraj, you were asking about that proof of Hahn-Banach theorem using extension of basis, right? So
Yeah. But I realized that mistake.
so
That
that will not work. I mean, because you see in the theorem we require that the norm should be same, right? So if you have any like G on W, and then we want to extend it to a bounded linear functional f, such that norm of f is same as norm of G, right? So you can look at very simple example, like even on R2 you can do. So if you say W is just the x-axis, right?
okay.
And then if I want to extend it, you said that, okay, we will extend it to any basis and then we will make it to be 0 on the rest of the thing, right? So suppose I take the basis to be E1 and E1 plus E2.
Okay.
Right.
Yeah.
So then what you are saying that, okay, so now suppose I take my linear functional on W is simply that you map G of E1 to be equal to 1, right? So if G of E1 is equal to 1, then that defines G on W, right? So basically G of T E1 is equal to T, where T is any scalar.
Yes,
Then the way you were thinking, then you will define F such that F of E1 is equal to 1 and F of E1 plus E2 is equal to 0. Right?
Actually, I was taking F. Oh, okay. Your basis elements are E1 and E1 plus E2.
Right.
Okay. Yes.
So then that will imply that F of E2 is actually equal to -1, right? So you are defining F of E1 equal to 1 and F of E2 equal to -1, and then you can easily calculate the norm of this. So this, because it is on finite dimension, of course it is a continuous linear functional, but then the norm of this you will see is equal to √2, not equal to 1, right? So
Yeah,
norm can
actually,
be
I
bigger.
realized that we need to take orthonormal basis only, but then we'll need Hilbert space.
Yeah. So you will need some more thing to be able to do that, because in general, the way like you extend, in fact, it need not be any even like bounded linear functional. So the continuity can also fail, right? So if you just extend it by putting it 0 on the rest of the basis element, then it need not even be continuous. So that is little more difficult to give example, but it can be shown that you can have such thing that when you extend like that, it is not a continuous functional. So therefore, I mean that will not work in general.
Yes, sir. Yeah, but it will work if we have a Hilbert space, and like if we have an inner product and we take an orthonormal basis only, then it might work.
Then also I have to see whether this will always work, because see what you need is that this basically if you take any vector v, then you can write it as W plus WO in the orthogonal complement, right? So V equal to W plus WO prime. Yeah, if you get it as like orthogonal decomposition, then it can be done, because in that case, you know that norm of V is always bigger than equal to norm of W, right?
Yes, sir. Yeah.
So,
That
but
property
the
was
thing
weak.
is that when it can be done. So, if your W is a finite dimensional subspace, then it can be done in any inner product space. It can be done, right? If you are in like Hilbert space, so if you allow W to be infinite dimensional also, then you need W to be closed. So that we will do when we discuss Hilbert spaces. So if we have a closed subspace of Hilbert space, then we can get V equal to W plus W per W prime, where W prime is in the orthogonal complement. And in that case, norm of V is always bigger than equal to norm of W. But that is not true in general Hilbert space also, if you don't assume W to be a closed subspace. So again, that Han-Banach theorem extension will work only if you assume W to be closed subspace.
Okay.
So there are difficulties that I mean, it is not like true even in general Hilbert space, because that best approximation, finding the orthogonal projection, that is not valid for any subspace.
Right.
So things can go wrong. So see, when you are thinking of examples, you think of only finite dimensional, and then you might think that it will work. But when you go to infinite dimension, then many things go wrong.
Yeah, and like even in finite dimensional, we imagine R square or R cube only. Like
Yeah,
I tend
right.
to imagine R cube always.
But it is good to always like try to think on your own, and then you will realize like, okay, what is wrong in No, of course, see, if there was like such simple proof, then I mean, people would have given it, right? So,
Yeah, there's a big name, so it might be
yeah,
like
yeah.
most
So
attributed.
one need to like understand like what will. I mean, one thing I can say that okay, like in the general this Hahn-Banach theorem, we use John's lemma, or equivalently we use axiom of choice, right? So one might think that okay, can it be proved for at least some space without using axiom of choice? So if
But
the
I was extending the basis, I was implicitly using this Zon's lemma over there also, because the proof of extension of basis also.
yeah, that is true, that assumes axiom of choice. But what I am saying is that the extension thing, you see that what I did was prove that if you have a subspace, then you can extend it to one dimension more. For that you don't need any like axiom of choice, right? So that way like you can extend it to finitely many also, and also for countably many. So if your space is separable, then this Hahn-Banach theorem, it can be proved without using this axiom of choice also. So in that case you will like extend one by one, and then by induction you can like do it for any countably many also. So that is one thing which is interesting, that without axiom of choice it can be done for separable like nonlinear space. Okay, anyway, so I'll stop now.